Okay, so before coming into the flood modeling, so what is your opinion? What is a model? How will you define a model? What is a model? Huh? Replica of a prototype. Okay, is any other? Simulate the physical process. Okay, any other? Mimic something. Okay. Okay, so this is like a simplified representation of a system. Simplified representation. So you can simplified representation can be in like a physical model or analog model or mathematical model. Physical model means huh? Physical model. So you are physically constructing. So like a spillway, a small replica of a spillway. We have one plume here to study the rainfall runoff process, groundwater recharge, etc. But now currently under maintenance. Physical model we are because here you have to check the similitude. You might have studied in your fluid mechanics, similarity laws, geometric similarity, dynamic similarity, those has to obey. So when you construct a physical model. So a sandbox model for groundwater flow is an example for physical model. Then what about analog model? From the name itself, analog. So something is analogous. So if suppose if I take the groundwater flow, what is the basic equation governing groundwater flow? What is Darcy's law? V is equal to K into I. Suppose if I take Ohm's law, what is Ohm's law? I is equal to V by R. So how it relates? V is equal to K into I is Darcy's law. V is equal to K into I. So I is equal to V by R. V by R. How it is related? I is related, current flow is related to V is velocity, current flow is related to velocity, and I is equal to V by R. V is voltage difference. It is related to what is I? I. V is equal to K into the Darcy's law. What is I? Hydraulic gradient. So what is the difference in the, suppose if you take two wells, what is the difference in the water levels in the two wells divided by the distance? So that is the hydraulic gradient that is related to voltage difference. 1 by R is related to 1 by R is related to in which quantity in Darcy's law, which parameter in Darcy's law? K. So hydraulic conductivity. So these are analogous quantities. So you instead of instead of representing the groundwater flow, you can represent it using electrical network and study the behavior of the network. So this seawater intrusion studies, Helesha model is an example for analogous model. So you can construct the electrical network and study the behavior, what is the current flow and all. You can then relate to the groundwater flow. Similarly, rainfall runoff modeling, one journal publication in natural hazards. Then, so what is the difference between hydrologic and hydraulic modeling? Okay, what is mathematical model? So I mentioned physical model, analog model, and mathematical model. What is mathematical model? So there you are representing it using mathematical equations. So based on the complexity of the equations, there are different solution techniques, analytical model, numerical model. Numerical itself, finite difference, finite element, finite volume methods. So what is analytical method? Huh? Close from or exact solution. So in simplified cases, suppose if it is a three-dimensional model, you can convert it into one-dimensional and simplify the equation, and you can directly use simple mathematics to solve the equation. So Thiem's equation in groundwater flow is an example for analytical solutions. Like that, you can just find out different solutions. And the other numerical methods, finite difference, finite element, finite volume, etc., are numerical techniques. And when it comes to the so flood modeling, hydrologic and hydraulic modeling. What is hydrologic model? You have experience in developing models technologically today. How many of you have experience? So then what is the difference, technologic and hydraulic?
Technology models, the models of input parameters which is one of the input, and this output acts as input for the hydraulic model.
Okay, so here in the hydraulic model what we are doing is we have the input data corresponding to that what is the outflow hydraulic. So means there are various characteristics which affect hydraulic, the land use and color changes, the soil parameters, watershed characteristics, all will affect the process. So that is hydraulic modeling. So for a particular rainfall, what is the corresponding hydrograph? So that is what you are getting from the hydraulic model. What is hydraulic model? So in flood inundation map preparation, so what you should know what is the depth of flow, what is the width of the flow, and the velocity through the channel. So in the channel, the depth, width, and the velocity, so that you will get it from the hydraulic models. Okay, so again mathematical model, different types of mathematical models. Physically based on physical, how will you derive the equations? Physically based means based on some physical processes. So how will you derive equations for the different processes? How will you derive? Based on certain laws. What are the different laws? Conservation of mass, conservation of momentum, and conservation of energy. So when you apply these principles, you can derive these different equations. So based on those kinds of models are known as physically based model. Conceptually, you are making a lot of assumptions. For example, watershed, you can consider like a tank and simulate the process. Those known as conceptual model. Empirical. Empirical means people will conduct experiment in the real field and develop equations. So those are known as empirical models. So in case of empirical models, you should be very careful about the units and also in which what conditions it is developed. So under that situations only you can apply those kinds of models. And then stochastic. So here you suppose in case of rainfall runoff simulation, you are giving rainfall as a probability distribution. So you will get different values, different outputs. Then based on spatial representation, lumped, semi-distributed, and distributed. So what is lumped model? So the entire area you are representing with one single characteristic. So you will get only one output at the outlet in this case, and the semi-distributed model like sub-watersheds. So in each sub-watershed you can get the discharge, then you have to route and get the final output. And in the distributed model you are divided into grid. Each grid you will get the output. Okay, so in each grid you have to give the parameters. So but the main problem with the distributed model, it needs lot of parameters, and if you don't have the data in no, if you don't have sufficient accurate data, then there is no need to develop this distributed model. What is event based and continuous models? So for a particular event, you are simulating, the other one continuous. So event-based model, there are based on the means there are a lot of applications. Event-based, what are the applications? So if you wanted to develop a design storm, what about the continuous model? Suppose if you wanted to develop reservoir operation, okay, this you need continuous data. So you can go for continuous models. Then, so this already I mentioned, based on solution techniques, mathematical models can be classified into analytical and numerical methods. Okay, so when you consider the history of rainfall runoff modeling or hydrologic modeling, the Peralt in 17th century, this was the first model. It is like an empirical model. He has conducted experiment in a watershed and found out that the annual runoff is equal to 1/6 times the annual rainfall. Then this was one of the major finding at that time. And by comparing the measured annual rainfall and the estimated annual stream flow, Peralt described the functional relationship as QA is equal to PA by 6. And Lindsley also confirmed the same equation in 1986. So some of the major important formula used various parts of India are Binnis percentage. You might have used these tables and standard charts, etc., for finding out the runoff. So these formulae are applicable to the region in which they are derived. So that is very important. So then an extensive acceleration of new discoveries in rainfall runoff modeling emerged with the digital revolution in 1960s, and numerical methods, statistical methods, and now currently AI and hybrid AI, hybrid techniques. So one of the most means in the earlier years, Stanford watershed model. There are various models, HSBF, basins, etc. And currently SWAT, Mike 11 NAM, WRF hydro, and big models are for hydrologic models. So how to select? We mentioned there are various softwares available to do the hydrologic model, and how to select which one will be suitable for your study. So typical features of the system, your study, your objectives of the study. Suppose if you want very accurate data, you have very good you have sufficient fund, then you can go for very commercial softwares like Mike 11 NAM, then degree of realism and availability of data and resources, and time scale of analysis. So what time scale you want to do the analysis. So when you consider the data for hydrologic modeling, rainfall data is one of the important data. So rainfall runoff modeling still depends heavily on the records from the point rain gauges. So but in Kerala, the main issue is, in the Western Ghats region, the data is very scarce. So actually IMD also have prepared the gridded data based on the station data, but due to the scarce nature of this data in the Western Ghats, the interpolation will not work out. Okay, so when you consider the IMD rainfall, when my student and the second PhD student, when he was doing for Kallada river basin, so when we calculate the annual rainfall for Kallada basin in the Western Ghats region, we were getting only 1,000, because in the Western Ghats region, definitely because of orographic precipitation, there will be good amount of rainfall. So then when we checked, the actual rain gauge station shows somewhat very high values, but in the IMD gridded data, it shows very less values because of the interpolation error. So you should be very careful when you use these kinds of data. And the source for this rainfall data is meteorological station or weather radar or satellite data. So we have some publications regarding the variability of the satellite data. This is not for hydrologic modeling, but it is for assessment of variability of rainfall erosivity. So how rainfall erosivity varies with respect to the different satellite data. So what we found out here is we have used IMD gridded data, IMD station data, then TRMM data, then CHIRP data. In that, CHIRP was underestimating and TRMM was giving very good correlation with the station data. So again, we corrected based on the observed data, we corrected the TRMM data and found out the erosivity values. This is published in Water Resources Management. And another thing is discharge data. So you, for calibration purpose, so when you develop a hydrologic model for a particular rainfall, what was the your observed rainfall discharge data, you should know. Then only you can calibrate, because calibration means you have to adjust the parameters. So when you consider the hydrologic model, there are various processes: canopy, then infiltration, then transformation methods, base flow. So there are various methods, and in each method there are various parameters. So you have to calibrate it during the calibration process. You have to adjust this parameter such that your simulated and observed data should match. Okay, so for that the discharge data is very important, and the source is India WRIS. And but sometimes when you get the data from download this data from, there will be lot of errors that you have to check it, because one time during a presentation, our MTech student, she was telling her in her basin the discharge is 5 lakh cubic. So do you think that is correct, 5 lakh? So what do you expect for a Kerala river, very short length river? What could be, and also very small rivers? What could be the average discharge? Hmm? What could be the average discharge? What about which river is having the highest discharge in world? Hmm? And what is the average value? Hmm? Any idea? What could be the maximum discharge still now observed? Any idea? So always you should check, and also you should compare, what about the values whenever you use your modeling. So Amazon having the highest discharge, it is more than 3 lakh. So in Kerala, we may get around 300 meter cube or 400 meter cube only. But she was telling she is getting 5 lakh meter cube per second. So, because whenever you use the data, you have to check the data. Here, when you download, there were a lot of errors, but if you actually purchase directly from the IDRB or any other agencies, that will not occur. I don't know whether it is intentionally created or how it has come. I'm not sure. Then other spatial data, digital elevation model is one of the important data in hydrologic modeling. Then land use, land cover, information about different land uses. Then soil data, soil property, mostly we use FAO soil data. And you can download these details from these websites. So digital elevation model, as I mentioned, one of the very important parameter, the data. So this, we have published paper in atmosphere from with Professor Sridhar. This was done by our BTech students. Okay. So here hydrologic and hydraulic modeling for flood risk assessment, and here we evaluated two different terms, and and found that the SRTM term was giving somewhat better results compared to the other one. So this hydrologic and hydraulic modeling, we have done it for the Periyar Basin. So we identified the best term and use it for hydrologic and hydraulic modeling. And the other one is suitability of different digital elevation models in the estimation of LS factor. It is not for hydrologic model, but we have estimated the suitability of different models like ALOS, Pulsar, Amsterdam, SRTM, Cartosat, and found out the LS factor and soil loss from these. And but here it was like a relative elevation. So whatever the term you use, there was not much difference. But when you compare the actual elevation details, if you see here, using Amsterdam 0 to 7.6 is the minimum value, but SRTM -8, it is somewhat reasonable, -8 to 7.6. But when it comes to Cartosat, it is minus 1024. So it is not at all reliable value. So you have to check, when you consider Kerala below, up to 4 meter, 6 meter, below mean sea level, 6 meter is okay. But 1000 and all, it is not correct values. The other maximum values are okay. But when it comes to the minimum values, but actual values, there are a lot of differences. Then other relevant data, temperature, evaporation, climate data, influencing the evapotranspiration, wind speed, solar radiation, all these you can download from these websites. Okay, so when it comes to the hydrologic modeling using HEC-HM, so various softwares use different techniques. Okay, so in order to convert precipitation to the hydrograph. Then here in the case of HEC-HMS, the precipitation, the canopy, surface means the storage, depression storages, the losses, mainly the infiltration, evaporation, etc. So for the calculating all these losses and the initial abstractions, there are different methods. You can see canopy, there are different methods in HEC-HMS. For loss, there are different methods. SCS curve number is one among them. So if you are using SCS curve number, you should have the geologic, hydrogeologic, what do you call the soil? What how will you call that? The soil how will you classify that in the case of curve number method? Is SCS curve number method? And no, anti-sediment condition is important. Then hydrologic soil group, hydrologic soil group grouped into 4 classes, and then that is based on that hydrologic soil group. How will you find out the curve number? Based on the land use and the soil type, and the new methods, the slope also important. So here based on the soil group and the land use, you can find out the curve number, then adjust for antecedent moisture conditions. So how the curve number varies? So if whatever the is falling on the ground, if it is going as runoff, what will be the curve number? Hmm? What will 100? It will be 100. So if all are infiltrating, it will be 0. So then Bayesian curve number method is one loss method, loss estimation method. Then we can find out what is the excess precipitation. Okay, so excess precipitation, and then this excess precipitation is converted into the direct runoff hydrograph. So direct runoff hydrograph means always it starts from 0 and ends at 0. So for a particular hydrograph, you can find out what is the direct runoff hydrograph. So here the base flow, the groundwater flow is not included. So finally you have to include the groundwater flow. Okay. So there are different methods to estimate the groundwater flow in HMS. So you can just go through each method, how it is different. Okay. For different initial abstraction and losses, there are different methods. Then for transformation, for converting the hydrograph into the direct runoff hydrograph, there are different methods. And then converting this direct runoff hydrograph into uh, uh, the total stream flow. Means, there are different methods. Means you have to add the base flow. So to estimate base flow, there are different methods. So you can just go through how it is different methods, how it is different. And then so when these you have to do it for each sub-basin. Then from each sub-basin you have to route. Okay, so route it, and there will be again in the reaches there will be again losses and gains. So that you should also consider, and then finally you can get the final discharge. So this is the process of hydrologic modeling in HMS. So again here for routing methods there are different methods, and there are loss and gain, there are different methods. So this is the basis of hydrologic modeling in HMS. So the schematic representation. So from the rainfall hydrograph, you can find out what is the excess precipitation by deducting the losses. Then this excess precipitation is converted into direct runoff hydrograph using transformation method, and then route for each reach you have to route it and produce the stream flow hydrograph. So this is the process in hydrologic modeling. So when it comes to the hydraulic model, so you know about this equation? Saint-Venant's equation. So the equation for continuity equation, which is based on the mass conservation and the momentum conservation. So here when you consider what is XC and XF, those who have already done the hydraulic modeling using HECRAS, what is XC? So if you consider here, compared to the other Saint-Venant original equation, here XC and XF, what are those? So the independent variable XC and XF, what are those in this equation? So here you are considering only the channel and its floodplain. So what is XC? So when you consider a channel, XC, then the floodplain XF. Okay. So XC and XF, the channel length and the floodplain length. Okay. So based on that, phi of the XC, XF, dou A by dou T. So how the cross section changes with time. Q is the discharge, so that should be known to you. Then, so what is dou Q by dou T? So you might have studied in your fluid mechanics. So it is a local acceleration term. The other one, convective acceleration. So here, this is derived based on conservation of momentum. So the net rate of change of momentum is equal to the net force. Based on that, you can derive this equation. So this equation is used for hydraulic model in HECRAS. So Saint-Venant actually derived this equation in 1871. So, but when it comes to the steady state, okay, so that equation converted into, what about this expression? What about this equation? Huh? It is the energy equation. So if you consider two sections, if you consider two sections, Z2 plus Y2 plus alpha into V2 square by 2G is the total head at total energy at section 2 and total energy at section 1. So here He is the head loss. So what are the different no, causes of head loss? Huh? So it can be friction loss due to the length of the channel, or there may be expansion. If you consider the turning, the curves and all, there will be losses. So those is represented by this tape. So C into alpha V2 square by 2G minus alpha 1 into V1 square by 2G. This is for expansion and contraction, and this is the friction loss. Okay. So SF bar, you might have, those who have already attended a course on the open channel hydraulics and hydrology, open channel hydraulics. So what is SF bar? The friction slope. So how will you find out the friction slope? From Manning's equation. So SF bar for two sections, suppose if you are considering this section and this section, SF bar is the friction slope, average friction slope between these two sections. So from this you can find out what is the head loss, and again you might have already studied the gradually varied flow profile computation. So what are the different methods of gradually varied flow profile? Direct step, standard step, etc. So here actually uses standard step method. Okay. So where you have to assume a particular no, by whether it is at the downstream, whether it is at the upstream, depends on the flow profile. Flow profile you have to assume. You have to assume a water depth. Then suppose the first thing when if you are doing a one-dimensional steady state or unsteady state flow in HECRAS is you have to digitize the central line of the river, then the banks, and then the floodplain. Okay, so usually the floodplain you have to ask, so what criteria they adopt for the floodplain determination. Sometimes they may find out the floodplain based on some particular return period. So that you can just ask your the state government agencies what return period they will found out the floodplain. So then based on that you have to delineate the floodplain and digitize the floodplain. And then one thing you have to remember is in the case of one-dimensional HECRAS is, so you have to digitize from the upstream side. Okay, from the upstream side towards the downstream side, you have to digitize, and then you have to give the cross sections. So when you take the cross sections, if you look from the upstream to downstream, so you have to digitize from the left side. Okay, so that is also important. So you have to digitize the river from the upstream side, the cross section from the left side. When you look towards the downstream side, you should start from here to here. So this is the way you can take the cross section. So you can even so usually this will take from the dump what you are giving, but you can also conduct a survey and give the actual elevation. So that will be the better way of finding out the cross sectional details. So here you can, this is the method. So using standard step method, you can find out what is Y2 by substituting by assuming a value of Y2. Okay, so the method is assume a value of Y2. So from the condition we are giving at the downstream side or upstream side, but it's not the profile that you can assume whether you have to give upstream side or downstream side. Suppose you are using a backwater, computing a backwater profile, then downstream side, what is the depth of flow, you will be knowing at the control section, then compute Y2. So that is the process. Based on standard step method, you have to compute Y2. So when you compute Y2, the assumed value should match with your computed value. So there you can give some tolerance and finally find out Y2. So this will go up to the upstream side. So this is what you are doing in the HECRAS, finding out the water levels, the Y2 or any other sections. So different sections. So first we will consider the two sections, find out Y2 here, then Y3 here. Like that it will go up to the upstream side. So this is the basis of the HECRAS model. Okay, so in the case of Suppose if you cannot apply the other one is energy equation. Suppose if you cannot apply energy equation, so can you give an example where you cannot apply energy equation? Huh? No, unsteady flow is different. So what about rapidly varied flow? Whether you can apply and why you cannot apply energy equation? So there are a lot of energy losses taking place and you cannot quantify the energy losses. So you have to apply the momentum equation there. So here you have in this case, if there is some hydraulic jump is occurring or from supercritical flow to subcritical flow, if flow is occurring, in that case lot of energy losses will happen. Then you cannot apply the simple energy equation. So in that case you have to go for the say invariance equation. So in the case of one dimensional, this also one dimensional, so only one independent variable x along x direction. Then the solution techniques is the implicit finite difference technique. So you have any idea what is implicit finite difference? So this invariance equation is converted into its algebraic equation. The partial differential equation is converted into algebraic equation using finite difference method. So do you have an exposure of computational techniques? How to do finite difference? So can you raise your hand? Only two. Okay. Okay. So suppose if I am taking a very simple equation, partial differential equation, dou c by dou t plus vx into dou c by dou x is equal to 0. So actually this is not related to invariance and all. Just I am taking a very simple equation, dou c by dou t plus dou vx dou c. What is the dependent variable? What is the independent variable here? Huh? C is the dependent variable, x and t are the independent variables. So how I can, this partial differential equation, how I can convert it into algebraic equation. So if I am taking explicit finite difference means it is forward in time. So you have to first create the grid. Suppose if I am considering it like this. So basically you are converting that differential equation into an algebraic equation. So here I am considering it as I plus 1. Along the x direction, I plus 1. What about if it is I plus 1, what is this one? I plus 2, I plus 3. Here I minus 1. Here if I am taking as j plus 1, this is, sorry, if I am taking as j, this is j plus 1, j plus 2. So in the case of uh, forward in time and backward in space, you can discretize as like c of I. So how will you discretize c of any parameter? Our dependent variable is c. The concentration at this node. What is the forward in time? So the forward in time means you are at the known point. That is one thing you have to remember. So forward in time, you are at the known point. So here, how you know the values of the dependent variable? From the initial condition. So at time t is equal to 0, you know the values. So you know all these nodes, you know the values. So it is the initial condition. From the initial condition, you know the values. And what about this one? From the boundary condition, you know these values. Okay. So here the variable is unknown here. So at the forward in time means you are at the known point. So how you can write it is the value at this node minus the value of this node divided by del x. So dou c by dou t you can convert it like, so value at this node minus value at this node divided by del t. Okay. So similarly, the forward, what about backward in space? Backward in space, you are coming backward. From here, you are coming backward. Okay. So based on this node, two nodes, you can write down the difference equation. You are converting the partial differential equation into different states. Okay. So like that, dou c by dou x is also you can convert and write down the equation, algebraic equation. So based on, suppose if you have a number of nodes, so based on whether it is explicit, suppose if you are writing it in terms of backward in time, backward means you are at the unknown point. So whenever you write the equations, you will get many unknowns. So based on the number of, this is not a implicit procedure. So when you try to solve, there will be based on the number of grids or number of nodes, there will be number of equations that you have to solve it simultaneously. So you have to use some Gauss-Jordan, Gauss elimination techniques to solve the simultaneous linear equations. In other case, explicit procedure, at one equation at a time, you can directly solve that. So this is the basis of finite. But you have to learn lot of things. This is very simple way of explaining. So this is this way the finite difference equation is solved and get the solution for different nodes. So this is in one dimension itself. If you cannot apply the energy equation, this is the way you are getting the solutions. And in the case of 2D, again in case of 2D, the solution is finite volume method. So this is the basis of HECRAS. So I will show you a demo in the afternoon. So how you can do the 2D. Okay, these are some of the papers, a hybrid artificial intelligence and semi-distributed. This is like a hybrid model, hydrologic modeling. So here we have the coupled HMS with the ANN model. And this is monthly surface runoff prediction using artificial intelligence. Then actually none of my PhD students are working on hydrologic or hydraulic modeling. One MTech student, Nita, she was working. She was a very good student. Even she published one paper and one is under review now. And one more we have to publish, 3 papers. She has done more than a PhD work, I feel. She was very good student and what she has done is she considered atmospheric rivers. She has done something on atmospheric rivers and also NWP models, and also she developed hydraulic model. Lot of things she has done, and but we published only one paper published, one almost ready, and no, I have to consolidate the other one. The modeling part I have to consolidate. So here the objective to analyze, actually she has taken a Spinachil River basin. She analyzed the contribution of atmospheric rivers to precipitation of in Kerala. Then there one NWP, this already published with Professor Sridhar, the second objective already published. Then the third objective I didn't do anything, I had to compile it. Then, so she in that study, she even considered many dumps, and even she was facing a lot of issues. Even some of the, when she used some dumps, even at the downstream side, she was not able to find out some of the streams which was already existing. So, you should be very careful when the flow accumulation, etc. When you do, you have to check whether it is matching with the actual stream network. Okay, so in one Alos pulsar and all, she was even the downstream side, many of the streams were missing, and also the shape of the catchment itself was something wrong. So everything she corrected. And SRTM was somewhat okay. Even Alos and FABDM, she was finding it difficult. And again, it depends on your study area. You have to check with the actual, the published watersheds. Then there were these were the rain gauge stations, and 3 discharge gauging sites were available. So okay, so then using the hydrologic model, he compared at the 3 gauging sites what about the hydrograph for the discharge data. Then she also statistical parameters she computed for different stations. Then we have in the HECRAS, we have also used the surveyed cross-section data. So actually this MTech work was also, the co-guide was from IDRB engineer. So he has given the data, the cross-sectional details, and we gave us input into the HECRAS model. And this, so this is she has developed the 2D model using HECRAS and given the boundary conditions and compared the flood inundation map obtained with the fuel map. And also for different years she has compared and also used NWP model for short time forecasting.